Hello everyone, this is Arturo Gomez speaking. I'm going to be your lecturer today in this virtual session about the tensile testing. At the end, after talking about the theory, we're gonna jump into an Excel spreadsheet and we're gonna learn how to analyze the data we collect from the machine. And the purpose of this test is to determine certain what is the behavior of the material once that you apply a certain uniaxial load, right? And how this material behaves, how this material deforms, and to obtain certain important properties that we can use in different engineering applications. Properties such as the Young modulus, such as the yield strength, the made strength, the failure strength, and so on, right? So let's summarize this by saying that the uniaxial tensile testing is done over a material specimen of this shape that you can see here that is in blue. This is a shape that is specifically designed in order to maintain a constant stress level across the specimen and to avoid the stress concentration in the analyzed region, right? That's the reason why we have this kind of bone shape, like a shape geometry, right? In which we have the central region, that is this one that I'm showing over here, in which we are going to measure what is the deformation and what are the stresses that are applied. And this a little bit more wider part in the top and on the bottom that are used to attach the test specimen to the grips of the machine, right? So this is a typical universal testing machine that we use to apply these loads. As you can see, we apply two vertical forces. Actually, I'm going to show you a video from one famous manufacturer of these machines. So those are the different kinds of universal testing machines. It varies from manufacturer to manufacturer, and it also varies depending on the range of forces and the material and the kind of material that we're going to apply. Right here, we have three different machines. This is more or less how this test is carried. As you can see, until yielding and fracture. Here we can identify certain or different parts of the machine. We have the test specimen, first of all, that is located in the middle, right? This test specimen is attached or is holded using tensile grips, right? So you can close them with your own hands. The purpose is that they are strongly attached and that there is no friction, that there is no delivery between them during the test. You have one grip on the bottom and one grip on the top. Usually, there is one of the grips that is movable, is the one that is displacing itself, and most of the time there is another one that is fixed. As you can see, there are some rails that allows the whole thing to move on. We can also have here an important part that is this load cell. This load cell is a sensor, is a force sensor that tells us what is the force that we're actually applying on the test specimen. This load cell is connected directly to a data collection system that it varies from manufacturer to manufacturer, but that helps us to collect and to record what is the history of the load that we're applying. On top of that, we have here an extensometer, right? That can be, well, there are different kinds of extensometers that we can use. And this is the sensor that we use to measure what is the displacement in the specimen, right? We can also use other different techniques. You can use strain gauges, and we can use also digital image correlation to obtain the same data, right? But those are at least the typical, most conventional parts, right? Here you can see a couple of test specimens. You may notice that some of them they have different shapes. Some of them are flat, and some of them are rounded, or they have a axisymmetric geometry. And it depends very much on the kind of machine that you're using and the kind of material that you are testing, right? So this shape, the size, and the thickness and the width of these tested specimens are very well defined in industrial standards, like this one, the ASTM E8, okay, that for these cases for metallic materials, right? It's important to remind that you always have to ensure that the test specimen is properly manufactured, is properly cut, and that you control the dimensions of this material. For that reason, we used to measure in 3 different points at least what is the thickness, right, of the specimen. Because if you have a smaller thickness or higher thickness, you will have different loads on the machine, or you will have different deformations on your specimen, right? In this case, they're using a micrometer to measure the thickness. If you have so far any question, you can definitely ask me. Yeah. Once that we apply this load or our testing specimen, the purpose is to obtain a curve, right? To obtain a curve of the load that we're applying, or the vertical axis, and the displacement, or the change in the length of the specimen, right? And at the end, we will get a curve that has more or less this shape. We'll go later in more detail about this. But, well, this is what we'll obtain. It's important that in the beginning, we have to identify an initial base length, okay? That this is the length that we're going to use to estimate the stress and the strain, or to convert this data from force into a stress data, right? So now that we started talking about the stress, we have 2 notions of stress and strain quantities. The first one is the engineering stress and strain quantities, right? Those are called engineering quantities because we used to use the simplified versions of what is really happening in the material, right? So in the case of the engineering stress, we can say that engineering stress is just taking the load that we're applying in newtons, let's say, and to divide this over the cross-section area, but the initial cross-section area, right, at the beginning of the testing. In the case of the engineering strain, what we have is the change in the length over the initial length that we were estimating in the beginning, right? The initial length, that's important. Both things are related to initial quantities, right? This is an example of the kind of curve that we can obtain from the engineering quantities. As you can see, those are 2 simple relationships. It's important to notice that we have different regions, right? We have an initial inelastic region in this part, and we have a plastic region over here. We'll go later in more detail. And we have a region in which the material reaches a maximum point, right? This is the region where necking, that is this contraction, I'm sorry, on the thickness of the specimen starts, right? You can see here on the image to the right that there is a deep decrease on the thickness of the specimen, that part, and this region is followed with the failure of the specimen when it breaks, right? So if we keep moving, we'll find that there are some other kind of stress and strain quantities that they are called the true or logarithmic stress and strain quantities, right? They're called true because they're more precise than the engineering quantities. And what I mean when I say precise is that they don't account that the cross-section area is going to be constant along the testing, right? As you can imagine, as the material is enlarged, is stretched, or is compressed in the case of compression, the cross-section area is going to change yeah, and it's going to change mainly because we have this Poisson effect, this Poisson ratio effect, in which the material changes his width or his cross-section area, or is reduced in the case of the tensile testing, right? So what happens with this is that if we have certain amount of force, certain amount of load, that in this case is represented with F here, divided in an area that is changing over the time, right? We're going to have a stress that is going to vary also, right? And it's going to vary in this proportion, right? So you have here that the true stress is going to be given by the force over the actual area or the instantaneous area. But this relationship can also expressed using the engineering quantities. So we can say that the true stress is given by the engineering stress times 1 plus the engineering strain, right? And it gives us a direct notion of what is the true stress of our material is, right? Where this mathematical relation comes from, it comes from the fact that the total volume of the specimen is maintained. And why it is maintained? Because in the case of most of the materials that we use in engineering, they have a constant density, and therefore the volume is maintained, right? If we keep doing the same analysis, we will find that there is also a true strain quantity, right? This true strain quantity is defined using the differential version of a strain, in which the differential of a strain is equal to the differential or the infinitesimal small change in the length over the instantaneous length. Also here is instantaneous length. We solve using this integral between 0 and epsilon. We'll find that our true strain is going to be given as the natural logarithm or the Neperian logarithm of the length over the initial length. But at the same time, using the same conservation of volume, we can arrive to this expression that is very useful at the end, in which the true strain is given by the natural logarithm of 1 plus the engineering strain, right? So those are the two equations that we're going to use, right? And here we'll find also similar, definitely a similar behavior. I would like to start by encouraging you to really remember two moving regions of the stress strain curve, right? The first one is this linear elastic region, and the other one is the plastic region. And we're going to talk about them right now. This first region is called the linear elastic region for two reasons. The first one is because the relationship between stress and strain is given by a linear relationship, right? Where the slope of this linear segment is the property E, that is the jump modulus, right? And it represents the stiffness, how hard or how easy it is to deform the material, right? We'll see that also this, in this material, if we start loading the material and in a specific time we reduce the load or we take out the load, we're going to recover the initial position of the material. So what I want to say is that the material returns to its initial position. That's the reason why it's called elastic, because it returns to its initial position. But we will see that this region will end in a certain specific load, and this load is called the yield stress or the yield strength, right? Yield point in this case, right? For certain materials, it's going to be the 0.2% of the strain. It's going to be somewhere over here, but it depends very much from material to material. So after this initial linear elastic region, we enter into a plastic region, and what it means is that there is going to be a certain amount of stresses that are not going to be recovered, right? So it means that we have a reversible process, and we can see easily here. Once that we increase our load beyond the yield stress, the material, first of all, is going to deform. Of course, it's going to deform. It's going to lose certain stiffness. You can see that the slope is way smaller. And what is important here is that once that I remove this load, material is not going to return to its initial position, but is going to unload, and is going to end at a certain strain, right? This is called the remaining plastic strain, and well, that's the main reason why we lose a certain amount of energy in this kind of process. It's also important to notice that if in certain scenarios in the plastic region, the material is going to keep increasing its load, right? But that region is called hardening behavior. But as we saw in the previous slide, the initial one actually, there's going to be some other regions in which the load will decrease, right? And this load, or this region, is called the softening region, right? So it's important to notice here also that once we unload and load again, for example, once that we have reached the plastic stress, the material is going to recover and is going to come back using a path that is parallel to the initial linear elastic path. Okay, what it means is that the material is going to return all its elastic energy, is going to be recovered, and for that reason, it's going to take this path that is parallel to this line. So in other words, the Young modulus is not going to change because we have passed the yield zone, right? So we're gonna jump now into talking a bit about the strain energy. So you very well know the meaning of strain energy, right? This strain energy is the energy that I need to deform a material, and has an energy itself is a work that I carried out, right? So this work that is carried out is given by the load that we're applying, right? And the deformation that we are achieving, right? And if we want to estimate what is the amount of energy that has taken to deform a material, we need to do the integral between 0, the initial position, and a certain deformation of this quantity, right? So in that sense, we can estimate what is the amount of the work we have applied, and that in certain ways, certain amount of energy that is stored in the material. It's important to notice here that we can divide this total amount of work into regions. First initial region that corresponds to the triangle given by A, B, and D. This triangle corresponds to the region that is required. I'm sorry, the energy that is required elastically the material. As you can see, this triangle here represents the total amount of energy minus the energy that is required to load the material within the slope that is the same than in the elastic region, right? And the other part, that is this one kind of purple over here, is going to be the region or the amount of work that is not recoverable. Is the amount of work that we can't recover because it has been used to deform the material in a plastic manner, right? So it's important because at the end, the total work that we applied with the machine, for example, with the universal testing machine, is going to be converted into a plastic deformation and an elastic deformation that you always recover. Yeah. We can do exactly the same analogy if we divide this by the amount of volume. What is the volume of our test specimen? Yeah, in our case, the volume is going to be given by the cross-section area and the longitude of the test specimen, right? And we will have this quantity that is the strain energy density. Yeah, at the end, this is the same approach. It's just density, because we're dividing by the total volume. This quantity is important because this quantity tells us many things about the material. It tells us about how efficient is the material to absorb energy, for example, during impact conditions. I think we've finished the theoretical part so far. If you have any questions related to that, I think it will be very convenient to do that before starting the Excel part. You have any question, please raise your hand here at the bottom, or write a message chat. All right, so I assume that everything is fine, and that yeah, you have more or less understood what I was mentioning. Now we're going to start with the analysis of some of the typical data that you may get from an universal testing machine, Uniaxial tensile testing. This is a more or less simple scenario, but it will definitely give you all the tools that you need to analyze future versions of this analysis. What we have here is different columns that we have to fill with the force, displacement, engineering, stress and strain, and the true stress and strain, right? And we have some material properties that we have to estimate, such as the Young modulus, the yield of stress, and the ultimate dimensions of our test specimen. Here we have, well, so here we have the force that is applied is given in tons, metric tons. So please bear in mind that the metric ton is 1,000 kilogram force that is equal to 9,800 newtons. We have here the displacement, and this displacement is the change in length, right? That's what I mean, change in length, delta L. And it's given in millimeters. We have here the dimensions. We have the width, that is 12.5 millimeters. We have the initial length of the specimen, that is 50 millimeters over here. And we know that the thickness is equal to 1.6 millimeters over here, right? And well, here we have also our equations. They're very important to remember. Here we have the engineering stress and strain, and the true stress and true strain, right? So let's get started by filling the engineering strain. So for doing it, the first thing that we're going to do is to click here on the first cell. We're going to double click, and we're going to write an equation, right? The equation that is in this part. So we're going to press equal, and we're going to say that the engineering strain is the change in position, that is the displacement, divided by the original length, equal to the displacement divided in the initial length. Remember, the initial length that we have. Okay. Here it is important to know that we're going to drag this cell down in order to fill all these values, but we want to maintain the initial length because the initial length is constant, right? So it's a constant. So for doing that, we press over the cell, that is this one, F4, the key F4, right? And as you can see, it will show you the dollar symbol before the letter and the dollar symbol before the number, right? You can also do that directly, writing the symbol, the dollar symbol, like pushing that F4 is like a shortcut for doing it, right? So once that we click that, we're going to see 0, of course, because we have 0 displacement, we have 0 strain, right? So now we're going to drag, and we're going to fill all these values. For doing this, we're going to, you can see here that there is a kind of square on the bottom right corner of the cell. So we're going to drag it down, we're going to click on it, we're going to drag it down till the end, and you will fill all the cells, right? If we double click somewhere at any cell, we can see that it's taking corresponding cell, but it's still taking the dimension that we want, right? Click escape. Okay. So we're going to do more or less the same thing, but now with the engineering stress. For doing that again, we double click on the cell, on the first cell, we press equal, and now remember that here we have that the stress, engineering stress, is equal to the normal force over the initial area. But the normal force here is given in tons, right? So we have to pass this from tons to newtons, right? So you already know that 1 metric ton is 1,000 kilograms of force and 9,800 newtons. So we can write, or we can click here on force, and we multiply by 9,800, right? And this is our force. And close it with bracket, that's okay. And now we have to divide it by the initial area, right? So we know that the initial area is the multiplication between the width and the thickness, right? I'm sorry, see, yeah, the width and the thickness are those two values. Yeah. As we can see here, these two values are given in millimeters. We also know that there is another convention for, or instead of using newtons for getting pascals, we can use Newton over millimeter square, and we will obtain quantities in megapascal. And this is a much easier way of dealing with material properties for structural purposes, right? At the end, what I want to tell you here is that if we use the area in millimeters, we'll obtain the stress in megapascals. That is very convenient. So we'll divide by the area, and the area will be given in millimeters. So we click here times here. And remember to press F4 to maintain, because remember that these two values are constant, right? Because we're talking about engineering stress at the moment. So if we close the bracket, it should look like that, right? And once that we have that, we click enter. Again, since the initial force is 0, or the initial stress is 0, and now we're going to drag again from the corner. We're going to drag it down, and we'll obtain this value. I think there is another question, someone? Now, guys, the next step, I would like to make a first plot of this engineering stress and strain relationship. So for doing this, please pay attention. I'm going to just move this a little bit to give space. So here in the Excel software, you have here different toolbars, and you'll have one tab that is called Insert, right? So go here to Insert, click Insertar, Insert, and go here in Graphs, Plots, and you click here in this kind of plot. Okay, that is the dispersion plot with the straight lines, with linear rectas. This one. So you click over here, and a new figure will appear. So far, it has to appear in white because we haven't selected anything. And sometimes if you select a row already or whatever, it will appear something over here, but ideally it should appear in white. So once, if you click on this figure, there is going to be a new tab that is going to be open. This is the design tab. So look at it over here. And on this tab, you're going to go to select data, this button on the top. You click for it, and there's going to be a new dialog box that will pop up. And you're going to create a new line, a new plot. So you're going to click on Add, Agregar, and it's going to tell you a couple of things. The first one, what is the name the name of the series or the name of the curve that you're doing. In our case, we're gonna write it engineering quantities. Let's write it like this. It can be any title, any name that you want. In this case, is engineering. And it asks you for what are the values on the x-axis and what are the values on the y-axis. So for the values on the x-axis, we're going to click in this button to select what are the cells that correspond to the x-axis. So we click over there, and we know that the x-axis is this strain. So we're going to drag all, and select all the whole column all the way down. And yeah, and we want, if once that we are done with this, we're going to return. So we click again this button, right? And now is the time to choose the y-axis, right? So we do exactly the same. We click here in the same button, and we're going to choose the stress. In this case is the y-axis. So again, we have to be very careful that we are selecting the same number of cells for both axes, right? So otherwise we'll have kind of different errors. So okay, we've already selected them. We click here to go back, and as you can see, it appears automatically. Okay, so click here in accept and accept here again. Right, so over there. Let's add the titles for the axis. I think it will be a good idea so far. So again, once we click, I think there was another question here. So I was telling you that now is a good time to put labels for the titles of the axis. So for doing it, we're going to click here again on the graph, and we're going to we're going to habilitate the design tab. So we're going to go to design, and on the left corner, we're going to click here on agregar elemento de gráfico, to add element of graph. So we click here, and we'll have titles for the axis, the horizontal title and the vertical title, right? So, and once that you have them here, you just need to click over here and to write whatever that it is. That in our case is strain for the x-axis and stress in megapascals. The y-axis. Please never forget to put the units in engineering works. There is nothing more bothering than doing something that doesn't have units. So it should look something like that. Okay. Well, before doing this, I would like you to check different things, right? The first one is that here we have our linear elastic segment, right? We have our hardening region over here and our softening region. And at the end, this point over here, we have our failure. Okay, so that's important to bear in mind. We can also change the size of the axis, or if you double click over the axis, will appear new options in Excel to change this length. So we can see that the range of the x-axis is from 0 up to 0.2, that corresponds to 20% strain. And we can also change, for example, what is the height of our y-axis. If we do exactly the same, we double click on the axis and we put limits. In our case, let's put 700 megapascals. Or not, 700 is too much. 600 is going to be right. Just right there. Also, different things. You always can go here into the bottom of this dialog window, and we can click here number, and it will give you the possibility of using different decimal positions. For example, if you want to use string, right? Or if you want, for example, in the case of a stress, since those are very large numbers, I think it would be okay to just use 0. decimal positions. But in the case, definitely in the case of strains, if we double click again there, probably will be convenient to use at least 2 or 3. Right? So in such a way that it looks a bit nicer. Okay, guys. I'm thinking before continuing, guys, it's gonna be almost 7. I know that. So I will give you 5 minutes of rest, so you can digest all this information, and some of you, those of you who want to also like a kind of clamp for the health professionals that are working at the hospitals, you can also have time for doing it. Okay, guys, we're back here. So I hope that most of you already went to Windows to clamp. All these people is doing a terrific job for all of us. So I think they deserve all of our recognition. So guys, so we're gonna complete the exercise that we have so far. So the next step is to fill the columns for the true stress and true strain, and to plot the corresponding graph and to obtain the properties. Right now, we're gonna use those equations to fill this column and this column. The procedure that we're going to follow is almost the same. So for the true stress over here, I'm going to click on the first cell, double click. So write equal, and we're going to write this equation, especially the last part of the last equation, right? That is in terms of the engineering strain. So the natural logarithm here in Excel is a function. It's a function itself, and you can write it as n ln. Right? If you write ln and you open the brackets, you can now put what is inside of the brackets. So it will be 1 plus the engineering strain. Right? The engineering strain. Well, as you know, it's this one. So we click for it, and don't forget to close the brackets. It should look something like that. Once that we click enter, of course, it's going to be 0 in the beginning, and now we can drag down to fill the rest of columns. Right? This is the advantage of this equation, that once that we have already calculated engineering quantities, from these engineering quantities, we can estimate the true quantities without the need of using the area and the length, because we used them before, right? So yeah, things are looking so far good. So now we can move into the true stress. We do exactly the same, equal, and we're going to write this part. So we have S, that S is our engineering stress. So click over here, multiplied by, we open brackets, 1 plus the, again, engineering strain, and close the brackets. Once we have that, as you can see, we don't have to put F4 anymore, right? Because all the cells are going to be tracked. So once we have this, we go all the way down, and we fill. If you want to reduce the number of decimal digits that you have, you can use this button over here, disminuir decimales, or decrease decimals. You can choose as many as you want. For this case, I think 1 will be okay. Same way that we have before. And yeah, unless for the true stress and strain, let's also leave like a 3. I think 3 will be 4 will be okay. Let's also put 4 over here. Right? Good. So we already filled these 2 columns. The next step is now to plot it over here. So again, we do exactly the same. So we click the figure that we created before. We go again to the design tab on the top of the screen, and we're gonna click in seleccionar datos, select data. We click there, and we are gonna add a new curve. So for doing this, we click in add, agregar. put a title on it. So these are true quantities, so put true. And we're going to click on the x-axis. I'm sorry, we're going to select now the x-axis data. That for our case will be the true strain. So don't forget to hold the click to drag the cells down. Right. Don't forget. And click here to return. And we'll do the same for the y-axis. Will be the true stress. We drag it down, take all the cells, and we come back. So as you can see here, there is something new that appears, a new graph. So we click accept, accept. Don't forget to click accept, because otherwise you will lose what you have done. And guys, here there is an important thing to take into account, right? The first one is that, as you can see, at very small strains below probably 2 or 3%, is this region, or here, we see that both the stress, the true and the engineering stress, they are almost the same, right? What it means is that for linear elastic purposes, it doesn't matter what kind of stress we're going to use, right? Because they're going to look like each other. There is no big deal. But as soon as we are starting to deform very much the material, they start to divert, right? As we can see, actually, I'm going to show you. I need to do something. Right? Yeah. As you can see over here, the engineering stress has a lower value than the true or stress verdadero, right? True stress, right? And there is a reason for that. There is a main reason for that, and is that since the engineering stress is always assuming that the initial cross section remains constant, we're gonna have a lower value than in the case of the true stress, because mainly on the true stress, we know that under tension, the cross section is going to be reduced. Once that we have that, now we can get our material properties. I will start with the yield stress and the ultimate strength, and at the end I will get the Young modulus. So let's remember that yield stress is the region where the material stops being linear elastic. So we can easily identify this point. This point is, if we go with the mouse and we put the mouse without clicking on this point, it will show us the coordinates of this point. In this case is 384 and 0.004, right? It corresponds to this cell, right? So you already know that. You always have to get DC values from the true stress and strain quantities, right? This is the most conservative manner of doing it. But as I told you, for the case of linear elastic region, it doesn't matter which one to use, because you're going to obtain almost the same result. Look, for example, here the difference is very small, like from 382 to 384. Okay, but the proper way is using the true stress, right? So what we do is we click. I'm going to open this a bit more. So we click again over this cell. We click equal, and we're going to select the value of the cell that we highlighted. Right. So we have here yield stress equal to 384 megapascals. For the ultimate tensile strength. So the ultimate tensile strength is the maximum value that you can get, right? In the true stress and strain curve. So in the kind of reddish curve that we have over here. So for doing it, we can use a function that Excel has to obtain the maximum value. So we click on the cell, put equal, and we're going to write max. And this max is for maximum. And this is a function that returns the maximum value from the selected cells. So we're going to open the brackets, and once that we open the brackets, we'll go all the way down on the true stress. close the brackets, and we click enter. It should look like this, and enter. And show us that the maximum value is 394. That corresponds to this value over here. You can also visualize these two values if you want. You just need to click on this point. You don't have to do that, it's just want to show you that you can also do different things with this. I think a triangle will look better. Yeah, like this. Right. And you can also do the same for the 494. So I think it's this one. Or I think it's this one. Yeah. So you go here, you click here on the marker, and you put it over there. Okay. So we already identified these 2 points on the graph. The remaining part is the Young modulus. There are 2 ways of estimating the Young modulus. The first one is the simple and the easiest one, and probably it's not my favorite one, but you can just take the slope from the initial point, the 0 point, and the yield point, right? So that at the end will be the slope, there will be the true stress, right, divided by the true strain. Remember that Young modulus is the slope, so it will be delta y over delta x, delta stress over delta strain. But since the initial stress and strain are 0, it will be simplified. And this is the value that we get, right? We will get 69,160 megapascals. This is a large value, and it corresponds, or is the same than saying 89.1 gigapascals. Usually, for most of the metallic materials, in fact, for most of the engineering materials, the Young modulus is in the order of gigapascals. So, in this case, we have 89. Gigapascals. Okay, so this is an option of doing it, but as I mentioned to you, it's not the best one. And well, and I will tell you why. It's mainly because in real scenarios, you don't have that perfect lines, right? So you may have. I'll just zoom in over here just to show you what I mean with that. Actually, maybe. In real applications, this is just the linear elastic part. Here we have more or less a straight line. It's almost a perfect line. But there are many engineering applications in which this thing will deviate a little bit from. It will look very much like a straight line, but it will deviate a little bit depending on the machinery that you're using. So in such a case, it's better to take a statistical approximation of this slope. So the easiest way of doing it is to get a regression line from this region and to obtain the equation of this line. So I will do that. You don't have to do it if you want, just pay attention, and yeah, after that you can ask me. A way of doing it is you can come here again. You can create another graph that we'll call linear part or linear region. And I'm going to choose only the linear elastic part, right? If you see, I'm only selecting up to here because I know that up to here is the linear elastic part, right? And now the same with the stress. So, and if I show you, if I take this out, it will appear on the linear elastic part of the true quantities. And now, after that, to obtain the regression line, I will click over it. I can go here to this small button that appears, click on it, and it will tell me, it will ask me if I want to include a tendency line. I will tell it yes, I want to, and I will go here to more options. We are extrapolating in that case, and it will show me to obtain the equation, right? So as you can see, the line of tendency is given by this equation, where our slope is this value, right? So as mentioned to you, in this case, our value is 87,246. That, if you notice, it deviates a little bit from the previous estimation or the simple estimation that we did. We'll also see that the point at which the line cuts the y-axis is not precisely 0. It's just a little bit more than 0. But as I told you, this is a statistical approach that is a better approach. Okay, guys. So I can just plot this again, just show you so nice it may look like. I'll just finish this just to show you the end of what curves may look like. And then okay, guys, so I think with this we're almost done. We already got our two curves, the engineering, the true, calculated the ultimate strength, yield strength, the tendency line with the Young modulus. So yeah. Okay, good. Okay, guys. So thank you very much for joining me in this session. I hope that you learned about this tensile testing experiment that probably you will carry out them a couple of times in your professional life. And if you have any other question or, I don't know, any doubt, you can write me to my email. It is in Aula Global.